Good morning, everybody. How are we doing today? Good morning. As I said, you people may not exist to me, so if you have to ask a question, be very obvious about it. I'm used to, being standing up front and whatnot, but they're trying to record things, and we want to celebrate them for doing that, so let's do it. This is Neural Networks in under an hour. As I mentioned to some people earlier before you came in, normally, as it said in the abstract, I actually try to type out the entire neural network, for the most part, during the session. These are 45-minute sessions, not hour-long sessions. So there will be a lot of just uncommenting out code because I don't have the time to type all this stuff out. Fair enough? Yep. Everybody okay with this? Cool. We'll quickly do a little bit about me. This does need to be updated, but the important parts are correct. I am a Microsoft MVP. Who cares about that, right? I do run the DevSpace Technical Conference, which is the one down in Huntsville that's kind of like this. We are on hiatus right now. There's reasons for that. It is coming back. I also work for Accenture. A couple other things that aren't on here. I am a Progress champion, so if you have any questions about Progress or Telerik products, please come talk to me. I'm also a Torque brand ambassador, so if you have any questions about those, please come and talk to me. But let's get into the meat of this. How much do you all know about neural networks? Somebody give me one or two people. What do you think they are? How do they work? And why would you use one? What are they good for?
Prediction.
What was that? Prediction? I mean, yeah, at the end of the day, they're all prediction algorithms. Or, taking in a subset of data and spitting out an answer. Go ahead.
Relationship mapping?
Relationship mapping? Yeah, you can use them very effectively for that. I was talking to my good friend Gary Short, who is a lot smarter on AI stuff than me. Let's give credit where credit's due. And he was explaining to somebody, and he came up with the best soundbite ever. When do you need a neural network? If somebody gives you a problem, and you can go, okay, we can solve this by doing this and doing this and doing this and doing that, you don't need a neural network because you know how to do it. When somebody says, I'm going to give you these inputs and I need these outputs, how can you give them to me? And you just go, you need a neural network. Because it's really good at saying, here are inputs, here are outputs, I have no idea what's in the middle, figure it out, right? That's what they're good for.
Is that unsupervised learning?
The way we're training it, it could be supervised, it could be unsupervised, it depends on whether or not you have a good data set to train it off of or not, things like that. There's also different ways you can train these things other than the one I'm going to use. I'm doing the kind of traditional old school way. Because I think if you understand that, then we can quickly have a hallway conversation and I can explain the other methods very quickly and easily and intuitively outside of that once you kind of know the basics. So we are going kind of low-level hardcore. So what is a neural network? Well, of course, everybody has seen the messy diagram, right? Everybody's seen that thing. What is it actually doing? Will this thing pick up if I walk over there?
I think so, yeah.
Probably. Okay, we're going to walk over here for a second. So we have some subset of inputs. That's why it's I1, I2, those are I's. We have some subset of inputs. We have some subset of hidden layers. For the purposes we're doing for this talk, I'm only going to use one hidden layer just to make the math easier, just to make the code a little smaller so we can get through it all. There can be multiple hidden layers. And then you have some sort of output layer that tells you what it thinks is happening. All of these connections are saying is that all your inputs get sent to all your hidden layers. All your hidden layers get sent to all your outputs after some processing is done inside of each layer. You have to be traditional because they're neural networks. What are each of those things called? Think in your brain.
Nodes.
Neurons is what I'm looking for. Synapses will take. Synapses would be more these parts. Right. Okay. So now, of course, we can get the slightly messier version. This is the biased messy diagram because what we generally do a lot of times is we have these things here, which are called your biases for each of the nodes. They come in to say, as the input comes in for this particular thing, we think this part is more important or less important than other parts. So that's where the bias comes from, right? We can, of course, on top of this, get the messy but slightly colored diagram. Okay, I promise you there are 4 different colors there. But I mean, with the red one, that's really all you need to see is that, it's going, all of the inputs are going to each of these nodes. And what it does is it says, for this node, these have independent weights on them, and it says that I think this input value counts this much towards what I'm trying to do. What is that hidden node trying to do? It's a trick question, I promise. You don't know, and that's the point. Nobody knows how these things work. Okay. I mean, they do know how these things work, but they don't. So then we get here, the messy but fully colorful diagram. See, now where all the colors coming in. Where they're each coming into each one and each going out. And of course, the biases will still be there when we're doing it. But that's basically all it is. You're saying take these inputs, figure out, and we're going to do this with the training, which ones are important or not, do some sort of processing on them, and then spit them based on what's important to our independent outputs. That's all we're doing. There can be more layers, there are more complicated things. At the end, I'm going to point you to a couple YouTube videos that does a great job of explaining what those hidden layers do, or what you think they're doing, and then what they're actually doing, and it's great. Anybody heard of a YouTuber, Three Brown One Blue? Yeah. He's got a really great visual explanation of all this that I have a link to in the code. Anyways, or in the slides. It's that one. And the slides, most of the slides are on my GitHub. We'll link to that at the end. All right, let's actually get into this thing because, you know, I just wasted 5 minutes on all that. Where did Visual Studio just decided to close? It's a good thing I didn't need that one to be pre-open and baked. This is the important one that had to stay open, that Firefox window. I need that one because this is the one that's been cooked. All right, so we basically here have a standard. It's in C#. It doesn't have to be in C#. It's the language that was quickest and easiest, and most people can read it pretty well because it's a standard C-type language. All of the weird stuff I'll get into. One thing that's weird at the top, just to mention, this is using a custom library I wrote, which is an open source project that does all sorts of math stuff in .NET. So I'm using my own custom linear algebra library. There's nothing special about it. Because of the way I needed to manipulate the matrices, the built-in .NET ones weren't enough. The DLL is included with the code, or you can go to the source project, which is also on my GitHub. If you really want to play around, if you really hate yourself, you can go get the raw library. I will warn you that it is completely in F# and other things. And it is very low-level manipulating bits, knowing exactly how inner workings of computers and math works inside in binary. You probably don't want to play with it if you don't want to play with it. We have one thing that's just going to come up later, print colorful. This is just something we're going to use at the end so that things look pretty, right? But we just have our standard made. There's only two files here. So there's our neural network, which is being separated, and there's our program. What do we need to use for, what do we need for our neural network? First and foremost, we need a question, right? I have a question pre-baked because I know it works. If we have time at the end, we can throw in different questions to see if it works. Sound good? There is one constraint to our question, which is, because if you get the version that's on GitHub after the fact, I have abstracted the fact that you can change the size of the layers and the code will adapt. Inside here for this demo, you better have 4 input parameters and 2 output parameters because all of the code for the training is hardwired, so it's easier for you guys to understand what's going on. Fair? So just know that when you go to GitHub, you're going to see a slightly different version. I think the version that's in here is a comment at the bottom of the file. But it looks a lot messier because it's actually doing things like dynamically checking for the sizes of the vectors and stuff like that. Don't worry about that. So, as we saying, this is our problem that we're going to train our neural net to do. It is a trinary XOR. Does anybody know how a trinary XOR works? Anybody know how an XOR above 2 parameters works? No? Let's see. This is when all that hardcore C when I was early in my career comes in advantage. No, XOR always returns if true if there are an odd number of truths. So if there's 3, there better be either 1 or 3. If there's 4, there better be 1 or 3. 2 and 4 don't work, etc., etc. So what we do here is we have 4 input variables, right, or inputs right there. 1 means it's true, 0 means it's false. Because neural networks really like numbers, not booleans. And I didn't want to add more complexity by having to actually write a function that turned a true into a 1 and a 0 into a false. Fair enough? So all these are saying, all right, if all 3 of the first ones are false, it's false. This is just starting to throw it for a loop because interesting things happen. We have a fourth parameter. The fourth parameter is fundamentally useless. It does absolutely nothing. Why would I want to do that? One, because when we actually go to train this thing, one of two things is going to happen. One, you will see when we look behind the covers that it successfully ignores the fourth parameter like it's supposed to. And that's awesome, right? Because it's like, cool, it's doing almost what we think it should do. You know what's even more fun? When it uses the fourth parameter, and that's when you really get to understand that you have no idea how these things work. Fair? So that is our input data, right? That's step one. All right. Now, unfortunately, we have to start to get into that scary word. What's the scary word? Starts with an M, ends with an ath, rhymes with maths. Yeah. Let's get into the math. Let's go back into our neural network. Here is our basic neural network. Oh, there they are. Okay. Here's our basic neural network. First of all, we got to get some stuff set up. This is where the first part of the math comes in. Control KU. Give it a second. All right. Here we have a bunch of functions. We're going to get back to those. We then have some helper functions here, right? I created a link-like expression that gives me a random value just because it doesn't matter what the initial inputs in all of your neural network things are, and they actually recommend that they're random, because if you try to make them something, it's just going to be wrong anyways, and it's going to take it longer to kind of figure things out. So just throwing a random number in there is all we want. So that's just a helper function to help us fill things in. We have the functions, which are going to be, let's go back to here for a second. This is what the hidden activation, hidden output, etc., are. Let's go back to our standard diagram. These are the functions that get executed right here to give you this value, and the functions that get executed right here to give you this value. If you notice, there were two versions of it. There were the input, and then, I don't remember what I called the other one, but there's a second version of it. The main one is for when you're going forward, and you're trying to actually, have the neural network give you an answer. The second one is for when you're going backwards, and you're trying to train the neural network. And now we get to that really scary word. This is where the calculus comes in. It is the derivative of the input function. We'll get into why in a minute. And we'll also get into all sorts of weird graphs. But that's where those come from. All right. So that's why we have the output and hidden activation, and we also have the prime version. The prime is the derivative. A little helper function that says, how do I take the results you give me and I turn it into something I care about? And then we have the main constructor that builds all the stuff, right? All right, let's go back into these. How is this thing working? This is where I'm going to be jumping back and forth for a second. Then I promise I'm going to be sitting for a while. All right, as we said, on our way forward, there's a function that runs here that takes all of these inputs and all of these weights and the bias, and it's going to produce a value. That value, as far as statistics is concerned, wants to be what? Somebody said something. Binary. Well,
True or false?
true. No, not necessarily true or false. Let's give you a hint. It's referring to something. It's referring to how probabilistic we care about this is.
Oh, it's a weight.
It's a weight, which would mean its value wants to be between 0 and 1, right? We really want a value between 0 and 1. Now, researchers have discovered that if you're in the utopian circumstances, aka all your input data matters, we actually can get around this and make it a lot more efficient. And instead of it having to use a very complex function we're going to get into a second that turns that value to between 0 and 1, you just kind of need to weight out the bad stuff. Right? So there are two functions that are built into the application. You can add any function you want as an activation function. Have fun, play around with the code. But you notice there's this first one called a sigmoid. What do you see that makes the sigmoid very unattractive? This is the actual equation right here. Not only is there an exponential, there's a negative exponential. So this is what the sigmoid looks like. Does a very good job of squishing. Is it going to let me zoom while I'm not online? It is. It does a very good job of getting everything between 0 and 1. And it has another fact we're going to get to in a second that is very appealing. But hold that thought. You can then also take the derivative of it, and it kind of makes it to where it only slightly changes the values as you go. And it also has another positive thing that we're not going to talk about quite yet down here. Can anybody tell what the positive thing down here we're not going to talk about is? Asymptote is what I was looking for. It never actually hits 0. Or at least if it does, it's so far out we don't care. Now, there is a lot easier function to use called a ReLU, or a rectified linear unit, which is the other one that's baked in. It says, return the value unless you're less than 0, and then just use 0. Very fast and effective to use. You don't have to do all this exponential fluff and all that other stuff. But it has a downside. Can anybody see the downside? What? Worse than that. That is true, but we can get around that. The bad part is, no, go back down here. The derivative for half of the cases is 0. That's the problem. The reason this becomes a problem is because if the derivative is 0 when you're doing the training function on the way back up, and all of a sudden the values you're getting for your derivative are 0, everything zeroes out and nothing changes. So if you're using stuff that you know everything's relevant and everything has a reasonable weight and nothing's ever going to be negative, ReLUs are a lot more performant. But if you don't know, or you know for a fact that some things are going to be deprioritized to where it's going to negate effects, you need to use a sigmoid or something that does not have the problem of ever hitting 0, because zeros are bad when you're multiplying things. Unless you're in school, then you like zeros because you know the answer. Right? So that's what those 4 functions are. So that's just our basic start, right? I don't think, we don't actually create the neural network yet. So now we need to use one of these and try to get it working. No, I think I do. Never mind, we get to actually see the neural network first. All right, I kind of asked this in advance. Anybody want to guess how big the actual neural network is? The code that I just scrolled off the screen. How many lines of code is it? I can do it in 1 line of code. You don't want to see that 1 line of code. To do it reasonably, how many lines of code is it?
No, 200.
What?
300.
300, wow. Depending on if you count the return value, 3. That is the entire neural network. Right there. So what is this doing? First of all, I need to explain another thing that comes in from my math library that didn't come from the dot net. This dot apply is a function that I wrote for my math library that says take this function and use it on every value of the array or the vector, or the vector or the matrix. So it's the same thing as like if you're doing, same thing as a map function, basically is what it is. But map was used for somewhere else because it's technically using other libraries where map was taken, which is why you use apply. So that's all apply is. We'll get to that in a second. Take the input, multiply it by all the input weights. What was the input weights up above? Are they still on here? Yep. What were the input weights? They're a matrix. Linear algebra. So matrix times a vector. Add the hidden biases to it. So now we've taken a matrix and a vector, the output of which will be a vector. We add the hidden biases, which are a vector, so the result is still a vector. And we apply the activation function to all of them. We're now in our hidden layer. So far, so good? Do the same thing to get from the hidden layer to the output. That is the entire neural network right there. And then I just return the resulting vector. This is just my little function that says, hey, here's how you take the data that was output and turn it into what we're expecting. It's the entire neural network right there. The only thing that looks weird if you're looking at this. Actually, who sees the one weird thing that's not weird, but I'll explain it. What is the inputs on the other side of the weights? Somebody here's got to know enough linear algebra. Matrices and vectors are very particular in what they'll produce.
Not commutative.
So yeah, they're not commutative. So just because traditionally speaking, vectors are 1 by n instead of n by 1, this is so that the sizes line up. So everything's slightly inversed, but that's just math in the background you don't have to worry about. That's the entire neural network. Want to see if it works? Sure. All right. Let's use some code. Let's go back to our main program. To step 4. Okay, you all are done with linear algebra now. Say, yay! We're still going to be using a lot of matrices and vectors, but that was the linear algebra. We're done. All right, so we're going to create our neural network. If you play around at home, these just have to match this. This is our function that tells us how to use our output. So what we're saying is that when we get to that output layer, we're taking 0, the 0th item to be true, and the first item to be false. Because it's going to output how sure it thinks that it's true and how sure it thinks it is that it's false. So we're saying whichever one you're more sure about, that's the answer. Make sense? So that's why our output function is, hey, is 0 bigger than 1? Is the first item bigger than the second item? That means it's more sure about true. That's all that is. We set up our activation function, so if you play around at home, just change these to whatever you want them to be. All they have to be is a function that takes a double and returns a double. After that, have fun. But you do have to know its derivative. How many of you do recreational calculus? Okay, see, another person very quietly raised their hand to where it couldn't be seen. All right, and then fairly straightforward, there's where my little print colorful comes in, just to make things easier to see on the screen. We're going to say, assume nothing's correct. We're going to look through. We're going to send each of the inputs. We're going to see whether or not it was correct based on what we know it should be, and then we're going to print out the results based on those random input values we brought in. Simple enough? How many are we going to get right? 70%. 70%? Wow. You have faith in random values being created by the compiler. Sweet. I probably am going to have to increase the size here. Because for some reason, Microsoft refuses to remember these font values. Can I edit? No. Oh, defaults.
Yeah, that works.
Go up to font. Let's go to 36. And of course it didn't do anything. Because I think it only does it once it actually runs it.
Yeah.
Anyway, let's hear. We have 1, 2, 3, 4, 5, 6, 7, 8 out of 16 red. So we got 50%. Not bad for untrained and random values, right? The funny part is, it thought everything was true. So basically we gave it input and it's like, yeah, you're good. Yeah, you're good. Don't you wish your boss was like this? It's very agreeable. Just, here's my inputs. Will this work? Yeah, you're good. Just go with it. So that did not work, just out of curiosity. See, now it's big. It remembered the defaults. And again, because they're the same value, actually they're not the same values. Why are they not the same values?
Different random values.
Different random values when I seeded it. And that's probably going to be too big when we get to the actual meat and potatoes. So let me drop that down a little bit. Let's try 28 when we get there. If I have to scroll, that's fine. But, all right. So now we need to train this thing. How do you train a neural network? Anybody have any sort of a clue? You're just not allowed to use the word backpropagation.
You adjust the weights somewhere, right?
Yes, you adjust the weights and biases. How do you do it?
The ones that gave you the right answer get increased, and the ones that gave you the wrong answer get decreased.
No, but that's a very good guess. Your heart's in the right place. Yeah, for those that didn't hear, his answer was you increase the weights on the ones that were correct, you decrease the weights on the ones that were incorrect. It's a very good guess. Anybody want to guess why that's wrong? No offense, that was a very good guess.
It could be, easy.
We don't want the ones that were correct to change.
Yep.
We want to change the ones that were wrong. And we want to change them proportionally to how wrong they were. Does all that make sense? So if it was close, so like the two were kind of near each other, we don't need to change it much. But if it really thought the other one was wrong, we really need to change things. Now, how do we determine what needs to change? Because how many values are we playing with here? This is a simple neural network. Let's do some quick math. This is just algebra. You're okay? How many values are we playing with here?
Three.
No. That would be lovely.
It's great.
So, there are 12 values in the input weights. There are 3 values in the input biases, so we're up to 15. There are 6 values in the output weights, and there are 2 values in the output biases. That's 28, I believe, my running total. So there's 28 values that we could change. How do we do this intelligently?
Do you have to figure out what the weights are?
No. You do not need to figure out what the weights are first. All right, we're going to use a trick. I'm going to say a very fancy calculus term, and then we will explain it in ways that make sense to other people, called a gradient descent. How many of you have heard of a gradient descent? Nobody. Okay, you have a couple people. Woo! What we're going to do is we're going to create a function, which is where all those derivatives come from. Because what do derivatives give you in terms of the original function? Slope. We'll take slope, right? We're going to produce a function which is the error function. We're going to produce a function that says, how wrong were we? We're then going to take that function, using all those lovely derivatives, and we're going to say, which way makes that number go down? And we're then going to tweak things so that the error goes down. So far, so good? Then we're going to say, let's figure those out and put them in there, and then we're going to do it for the next layer. Based on what that said, how wrong was it? Let's tweak those so that the error completely goes down. The beauty of this is if it wasn't very wrong, it's not going to change it very much. If it was really wrong and there's a high slope there, it's going to change it a lot. Now, why don't we do something smart and say, well, if we know we're here and we're going down, why don't we just track the value until we find where it zeroes off, right? That would be smart, right? Why do we not do that?
Nobody knew.
What was that?
Overreact.
Overreact? Yes and no. It is a side effect of overreacting. Y'all can wrap your head. You're doing the right thing there. Yes.
Okay.
Yeah. You don't want to get stuck in a local minimum. You have to remember that your brain is wired to thinking in 2-dimensional graphs, maybe 3-dimensional graphs, because you are not math people. Not only do I have a master's in artificial intelligence, I have a bachelor's in abstract math. I am particularly wired for this problem. How many output weights and whatnot do we have? We just went over it. 28. So now we're talking about a graph in 28-dimensional space. How many of you can wrap your head around that? No, not so much. A little bit. You have a, 0. So we're still doing that thing, but that is not going to be a nice little 3D like slope out or what we were looking at in Desmos there a second ago. No, this is a nasty thing with lots of hoops and burrs and spikes and all sorts of stuff. We want to slowly nudge towards the right value, going quickly if it's a huge steep, going softly, because we're trying to avoid those little local minimums, those little places where there's a little bump, and not get stuck in those things. Because if you get stuck in one of those, all of a sudden the network never converges. Yay, I was talking too much. Wake up. Maybe I'll rename my computer Little Susie. No way. Okay, a few people got the reference. Thank you. Oh, I have to press the red button again? Wow. It didn't like it going to sleep. They're trying to record all this. All right, so that means now we need to train this thing. So let's look at this training algorithm. It's not quite the 4th of July, but here comes your fireworks. Bloop, here's our training function. There's an extra semicolon because everybody needs an extra one just in case. I don't know why it's there, sorry. First thing we're going to do is we have a couple of vectors to calculate our errors for the hidden bias, and then we have a couple matrices to do our other part, right? So we just have holding places as we're doing this calculation. Here's the thing. We need to know what we expected it to be and what it actually was. Basically, right here, I recreate the neural network. Yes, I could have just called it, but I actually needed the values from the hidden layer for later. That's why I do it manually, is I need to know what those intermediate values were. So that's why I'm calling it myself. Yes, I could have done things where it's in some sort of property and I can access it later and whatnot, but this is demo code. We good with demo code? Yeah. So just know if you start really playing around with this code, you need to change it 2 places. Right. And we get to decide outcome. We then try to get the global error. What's the global error? This is not a trick question, I promise. We're trying to say how wrong were we overall. This is what we expected for true was that output 0 would be 1 and output 1 would be 0. Right? That's what we expected. So how off are those based on what actually came out? That's our global error. Because that's going to tell us which side of the equation was most wrong. So we get our global error for that independent node. We then say, we think this thing was wrong by, let's just say, picking a number, 25%. It's 25% wrong. So we then come through and we say that's where our errors were with the output basis. And we multiply that times everything that came into it. So we say you are off by this much, plus or minus. So tweak the values that much. So make it 25% smaller, make it 25% bigger, depending on which way off it is. We then propagate those errors into the activation layer. And say, well, if it was 25% off here, that changed it by this much actually inside that actual layer. So we need to change the outputs this much to tweak it that much. So we're pushing back propagation. We're propagating the error back through, splitting up its individual components into where it actually goes. Push it through all the way to our hidden weights. So that's what we're doing. That's what that derivative is for. It's the slope. Which direction is it going? Right.
Decreasing.
So is it decreasing? Is it increasing? Do we need to make the values go up or down based on that value? How much does it change? Do we need to push it a lot? Do we need to push it a little? All of that. That's how we're pushing all these values through. We then, as we come through, store them all, and we just add them into what we're doing. At the end, I take for all of the values, some of these I needed to push a little, some of these I needed to push a lot. I then average out the value. How much did I really need to change it by? This guy said it needed to change by 50%, this guy said it needed to be changed by 20%, this guy said by 1%. All of that put together, I need to change it by this much in this direction. I then apply that to all of our weights. And then we try again. We see if we got any better. And we then repeat this over and over, passing in our values, seeing how right we were, correcting, trying again, until we get the results we want. Simple, right? How long do you think this will take?
A minute.
A what?
A minute.
A minute?
Southern minute.
Actually, depending on factors, a minute could be correct. That's not what I'm looking for. How many attempts do you think it's going to take?
Couple three.
Couple, three?
Yeah, it's a little mess of a passel, possible clip or
Possible plethora. I'll give you a hint. Remember how I said that it gets interesting, which is why I'm glad we kind of have time to do this a couple times? Whether or not it figures out that first value is correct or not, or that fourth value is not needed. If it figures out the fourth value is not needed, it averages between 50 and 60,000 iterations through the loop before it gets everything correct. Because we're trying to slowly nudge it and correct things as we go along. Right? And that takes 30-ish seconds. If it thinks the fourth parameter is interesting, we're generally up closer to 150,000.
So, you're talking about, I understand how long we can evaluate how long the output values are. How do you evaluate the weights of the synapses, of the contributing components based on the next layer back? How do you know how long that is?
So I did explain that I did a horrible job of it, so I will do better. Thank you.
Does that weight, that single weight propagate through all the leads to it?
Right, so this is the basic idea. Let's go back here. We come here, we say we expected this to be 1, we expected this to be 0. Let's say this was, let's say we were correct, so we don't need to change things much. But let's say this was 0.95, and we said this was, let's even be extreme about it. Let's say that they thought this was 0.5. Right, so this is quote-unquote 50% wrong. This is only 5% wrong. It then comes through and says, as we're doing the back propagation here, our global error is only 5%, so these don't need to change much. This, it said, this was 50% wrong and needs to go down. These are going to change more. But then when it gets to here, it still has that global error, but it then can split up to saying, how wrong were these sides to get this closer to what we expected? So it's kind of taking that 50%, putting it here, and then this will take the individual pieces and say, okay, out of that 50%, I'm responsible for 20% of that, I'm responsible for 5% of that, I'm responsible for 25% of that. And so these are getting affected more than these because those were closer to what the values they expected. Right, so it's kind of sharing the blame and pushing the blame back and moving things. So these will move a lot slower than these, because these get a big dose of the error, these get a lot little. And it's why a lot of these things, they say some of these LLMs, which are all neural networks in the background, take months and months to train. It's because those first few nodes change very slowly. And they have developed tricks where you can train an individual mid-step, but that's well beyond the scope. Now we're talking into math you don't want to touch. Did you want to touch the math we've touched already? Okay, we have one person. But you don't want to touch it. Couple people. Yes.
I do have a question.
Okay.
You keep talking about taking the first derivatives to get the directional trend, right? So it's dropping, is it increasing, is it level set, whatever. Is there, I'm not hearing you talk about the second derivative where you get an idea of the rate of change. I mean, is there a return on investment for that?
No.
Okay.
Yeah, I mean, every time you take a derivative, you're getting the rate of change of something. So you have an original function, you take the derivative, you get how fast it's changing at that point.
Yeah.
You take the second derivative, you get how fast the change is changing.
Yeah.
We don't need that many turtles. Right? Yes, there are turtles all the way down, and like if you're in physics, the difference between speed and velocity and acceleration and all that other stuff, or distance, velocity, acceleration. The acceleration doesn't matter. We just need to know. I need to go this way because this will minimize the error. Just push me that way. I don't care how fast it's going down there because the slope will handle that. Because I just need it as a scalar vector that I'm going to push through, or a scalar value.
Okay. Yeah.
Okay. All right, so let's wire up this thing to actually do it. So now we're going to come over here, step 6. All we're going to do, epoch is just a fancy math word for what iteration are we on. Sorry. Not sorry. We're going to say for the epoch, we're going to keep track of the epoch. Because at the top, there'll be a counter that says how many epochs we're going on. And we're going to do it, and then we're going to count to see how many we got right. If we didn't get them all right, we're going to eventually update the epoch. We only update the screen on the epoch every 1,000 tries. That should tell you something. That way that number isn't moving too much and flashing too much. Every 1,000 tries, we're going to update everything. We're going to say how many were correct at that point, and then we're going to come down here and we're going to do something you're not really supposed to do because nobody cares what's going on inside the network, right? Right? We do go in there and we say, print out the network so we can see the values. Because this fun is an educational experience. We're doing something this small to actually see what's going on. And I can show you what I mean by whether or not it thinks the fourth parameter is useful. And then we're going to train, we're going to add, we're going to see if we're correct. And we're going to keep doing it until we get all 16 to be correct. Normally you would never want to do this. Why would you never want to do this? It's not that computationally intensive.
Overfitting.
Overfitting. If you give it the same data over and over, it will get really good at figuring out how to deal with that data. I can do this in this case because I have a fixed number of inputs it can be. So I can train it until it knows exactly what it's doing then. If you're doing something like image classification, if you always give it the same images and always train it to those same images, it's going to get really good at those images, and it's not going to know what to do with any other image. So typically what you do is you train it on a subset of the good data you have, and then you test, excuse me, you test it against the set you pulled out. And if that set's correct, then you're like, we're good enough for now. But if it's not correct, you then pull out a different subset to train on, and then test on that different subset, so that you're changing the inputs in which you're testing against, so that it doesn't overfit to just that data, which means if you give it new novel data, it won't just go, that wasn't in the training set, so I don't know. Because that's what will happen if you do these things naturally. So, but we don't have that problem. All right, let's run this thing. Let's see what happens. Boop. Now I get the benefit where if it size isn't, that size looks pretty good. All right, you ready? Here it goes. Dun, 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 dun. All right, we're up to epoch 30,000 now. You see the values are slightly changing. Weird things are happening. We're getting worse. All right, we found them all. 83,340 epoch. Let's trend what happened. First of all, yeah, we did pretty good. This is all the stuff that's coming in from that fourth parameter. Notice they're all very small numbers, or negative numbers. So it did kind of figure out, in the long run, this thing's doing nothing. Weird things are, for some reason, it really thought the middle parameter was doing something kind of funky. I don't know why. And at the end, it said we need a lot more assuredness on the true side than the false side. That's kind of interesting. Why is that interesting? It said, we care about how certain we were it was true. We don't care how certain it was false. It almost turned that off. Because it's like a negative close to zero. Alright, it's just kind of knowing how to read some of those lines. And if we do this again, now keep in mind, if I ran this now with those weights over and over again, it would always be correct. Because this has been trained to take those inputs and produce those outputs. But if I run it again, which is going to change the random input variables. Right, y'all remember roughly where it was at. Oh, yeah. Notice, here's where it thought there were very important things. Still kind of figured out this was important. It actually even more figured out it was important because it deprioritized all of them. It said just remove them basically from our classification. And now it thought the false side was more important. Remember that part at the beginning when I said the cool thing about these is we have no idea how they work? Yeah! So in the slide deck, that 3 blue, 1 brown playlist that I have linked to, I don't remember how many videos up to now. When I originally wrote this talk, there were 4 videos. I think he's added the LLM ones into the playlist, so there may be more now. But what he does, which is great, is he does a visualization where he's talking about the algorithm the United States Postal Office created to scan, take inputs of characters from people's handwriting of the zip code and figuring out what numbers are. So he's trying to classify from an image what number it is. So far, so good. And so he sets up this neural network that says it has this many inputs. And it's something like, because I think it's a 16 by 16 image, so it's like, what, 256 inputs? Something outrageous like that. This is the input, which squishes down into 9, which then crosses over into 9, which then outputs into 9, or something like that. But he's kind of like, this is what I imagine it's doing. We're going to take the raw thing, and then the first part is going to mask off certain sections of the image for certain features. So it's going, I want to know what's going on here, is what it's doing. So it's turning off all the other pieces of the input and saying, I just want right here. This is what he's imagining. And then it goes into the second side. And the second side says, we're going to classify how filled in this area is. So imagine, old school clocks and whatnot, how you had the what is it, seven digit or 7 display, where you got the 7 LEDs that can create numbers based on the lines. Basically, he's taking the numbers and he's dividing areas into lines and saying, how much is that line there? Based on that, it's probably this number. If it's got one here and one here, but none in the other places, it's 1, etc., etc. And that's what he visualizes is going on. And he does this really cool visualization where he flows through the network and he shows that's what's going on. And then he trains his network. And then he shows what the network's actually doing. And it's a hot mess with things all over the place and absolutely, it's like complete scatterbrain. No human can ever look at what it does. But he's like, I can pass in any number to it and it will figure out what it is. Okay, we have no idea what these things are doing. You can try to create these guesses of how you think you might want to deal with it to kind of decide how many input, hidden layers you need and what size they need to be. But you really have no clue. It's going to come up with something new and unique and novel, which is what makes neural networks really good for certain types of problems. Because they can find patterns and statistics and data that you would have no chance of ever figuring out the little nuances in. We are over on time. I am more than happy to stand around here and talk more about this stuff and go into some of the other things and whatnot. Here's this. Go up one. Okay, here's this part. Most of this stuff is correct. I'm very rarely on Mastodon anymore, but you can find me on Blue Sky, same username. But yeah, all of that stuff can get you to where you can find me if you want to track me down. Find out the GitHub's in there. The name of the repo is DIYNN. Do-it-yourself neural networks. The version of the slide deck up to here is in there. So this reference one is in there. I'll update that when I get home, so it's got the Desmos screenshots, just so you see what those functions are doing. Any questions? I will stick around for a while. Anybody who wants to run away to go get a head start on lunch, please do. I do not come between people and their food, or else I become food. I understand this. But thank you all for showing. I hope you all learned something, understand what's going on.